Hi student, welcome to my channel Education Shop. In this video, solve problem 3.73 from the book Fundamental of Heat and Mass Transfer by Propera 7th edition. Here the statement of the problem. The energy transfer from the anterior chambers of the eye through the cornea varies considerably depending on whether a contact lens is worn. Treat the eye as a spherical system and assume the system to be at a steady state. The convection coefficient H0 is unchanged with and without the contact lens in place. The cornea and the lens cover 1/3 of the spherical surface area. The values of the parameter representing the situation are as follows. R1 is the inner radius of this anterior chamber that is filled with fluid, and its internal convection heat transfer coefficient is Hi, and its value is provided, that is 12 watt per meter square dot Kelvin. The R1 value is 10.2 millimeters. 10.2 millimeter means that the radius of the first layer on the anterior chambers, and its thermal conductivity is K1. The R2 is 12.7 millimeters, mean to say 12.7 multiplied 10 to the power minus 3 meter. And the R3 values. R3 is the radius from the anterior chamber till its outer surface. R3 is the radius of the second layer from its centers of the anterior chamber till its outer surface of the contact lens. And thermal conductivity is K2, that is 16.5 millimeters, mean to say 16.5 multiplied 10 to the power minus 5, 10 to the power minus 3 meter. The inside temperatures of the anterior chamber is T infinity I, that is 37 centigrade, and the outside temperatures outside these two layers, the first layer cornea and the second layer is the contact lens, and its outside temperature is T infinity 2, and that is 21 centigrade. The inside temperature is higher, the anterior chamber's temperature is higher than the outside temperature. That's why the heat transfer is occur from higher towards lower. The thermal conductivity of the first layer is K1, that is 0.35 watt per meter dot Kelvin, and the thermal conductivity of the second layer, that is contact lens, that is K2, is 0.8 watt per meter Kelvin. And the convection heat transfer coefficient outside the contact lens is H0 and is 6 watt per meter square dot Kelvin. So all the required parameters are given and provided. Based on these parameters, we need to calculate the amount of heat transfer from these anterior chambers of the eye when there is lens provided, when there is no lens provided. So we need to calculate the amount of heat transfer from it without the contact of lens and with the contact of lens. These are the data that is provided. Now what we need to find, the required data: amount of heat transfer without the contact of lens, amount of heat transfer with contact of lens. This is without contact of lens and this is with contact of lens. Before finding the amount of heat transfer without the contact of lens, I will draw the diagram that is required for it. Anterior chamber radius is R1. The first layer, that is called cornea, its radius is R2, and its thermal conductivity is K1. This is the first case on which the contact lens is not provided over the cornea. First thing that is need to find is the anterior surface area. The internal surface area of the cornea is AI. Since it is 1/3, we are considering the 1/3 area, so it is 1 over into area 4 pi R1 square. The R1 value is, simply solve this on calculator, you will get the internal surface area of the cornea is, that is 4.358 multiplied 10 to the power minus 4 meter square. And the outer surface area, again 1/3, 4 pi R2 square. R2 value is 12.7 millimeter. Just solve this on calculator, so you will get the A0 value, that is 6.756 multiplied 10 to the power minus 4 meter square. Now let me draw the thermal resistance network diagram for the first case when there is no contact lens provided over the cornea. First, the heat is transferred from anterior chamber to the surface of this cornea, and the mode of heat transfers is convection heat transfer, and the resistance that is occur is Ri. Temperature is T infinity I, resistance Ri, because here convection heat transfer is Hi, here the convection heat transfer outside the cornea is H0, and this layer, the corneal layer, which thermal conductivity is K1, also offers some resistance to the heat transfer, that is R1, and finally resistance R0 outside the cornea, and the temperature reaches to T infinity 2. Now the Ri value is equal to 1 divided by HIAI, that is equal to 1 divided by what is Hi value, that is 12. AI value is 4.358 multiplied 10 to the power minus 4. Let's solve this on calculators and you will get the Ri value, that is 191.22 Kelvin per watt. Next is the R0 value, that is equal to 1 divided by H0 A0. H0 is 6 multiply A0, that is 6.756 multiplied 10 to the power minus 4. Simply solve on calculators and you will get the R0 value outside the cornea resistance to the heat transfer, that is 246.7 Kelvin per watt. This is the R1 value. R1 is the resistance that is offered by this spherical shape of the cornea. Resistance offered to the heat transfer by this spherical shape of the cornea. Remember, but this spherical shape of the cornea is 1/3, not the whole sphere. Just portion of the sphere means 1/3. This is the 1/3 portion. So total resistance for the spherical shape is equal to 1 divided by 4 pi K1 into 1 divided by R1 minus 1 divided by R2. This resistance is for the whole spherical shape of the cornea, but it is only 1/3, that's why we will divide by 3. So it's a simple math rule. These 3 will move from bottom to top, so I can write like this: 3 into 1 divided by 4 pi K1 into 1 divided by R1 minus 1 divided by R2. Now just simply put the value and solve this on calculator. The value of K1 is 0.35 and the R1 value is 10.2 minus 1 divided by 12.7 into 1 divided by 10 to the power minus 3, because it is in millimeter, so take 10 to the power minus 3 as common outside. Now solve this on calculator. Now press this equal button and you will get the R1 value, that is 13.16 Kelvin per watt. Let me write on the notebook. Now simply the total resistance, the total thermal resistance of this network is Ri, R1, R0. We simply add the values. We simply add and you will get the R value. So the amount of heat transfer without lens is equal to change in temperature divided by total resistance between these two temperatures. Change in temperature is T infinity 1 minus T infinity 2 divided by total thermal resistance between it, and this inside temperature is 37, outside temperature is 21, divide with the thermal resistance 451.1. solve this on calculators. You will get the amount of heat transfer without lens, that is equal to 0.0354 watt. Multiply with 1000 and you will get in the amount of heat transfer without lens, that is 35.4 milliwatt. Now let's come toward the second case, when the contact lens is provided over the cornea. Let me draw its diagram for the sake of simplicity. This is the first lens whose internal radius is R1, the outside radius is R2, and its thermal conductivity is K1. Then the contact lens is provided over this first layer and its thermal conductivity is K2 and its radius is R2, R3. Inside convection heat transfer coefficient is H. Inside convection heat transfer coefficient is Hi, outside is H0. Temperature here is T infinity 2. Here the temperature is T infinity 1. Now let me draw the thermal resistance network diagram, and there is 2 layers, 37 centigrade, and the outside temperature is 21 centigrade. And the heat transfer reaches from this point to the interior surface of the cornea. It offers some resistance, that is Ri, resistance Ri to the heat transfers, then resistance to the heat transfer is offered by this first layer of the cornea. The first layer, that is called cornea, that is R1, and the second resistance is R2, that is offered by this contact lens provided over this cornea. And finally, heat is transferred outside the point where the temperature drops to 21 centigrade, and the resistance offered outside this contact lens is R0. And finally, the temperature dropped to T infinity 2, where the temperature inside temperature is T infinity 1, that is 37 centigrade, and here is 21 centigrade. In the first case, we calculated the Ri value. That is same in the second case also, that is 191.22 Kelvin per watt. And the resistance R1 of the first layer, that is 13.16 Kelvin per watt, is the same as we calculated in the previous case. Next, we need to find the R2, that is equal to 1 divided by 4 pi K2, thermal conductivity of the second layer, 1 divided by R2 resistance minus 1 divided by R3. Since this resistance is for the whole spherical object, but it is 1/3, that's why we divide it by 3 to get the resistance only to 1/3 portions. By rearranging, we can write it like this. The value of K2 is provided, that is 0.8, and the R2 value is 12.7, and the R3 value is 16.5 millimeter. Tag 1 over 10 to the power minus 3 as common. Just solve this on calculator and you will get the R2 value, that is 5.41 Kelvin per watt. Next, we need to find the A0 value when the contact lens is provided over the cornea, that is 1 over 3 4 pi 1 over 3, because our study is under the consideration of 1/3 portion, that's why we divide it by 3, 4 pi R3 square. The R3 value is 16.5 millimeter. 16.5 multiply 10 to the power minus 3. Just solve this on calculator and you will get the A0 value, that is 1.14 multiply 10 to the power minus 3 meter square. And R0 is equal to 1 divided by H0 A0. 1 divided by H0 is 6, multiply the A0 value is 1.14 multiply 10 to the power minus 3. The solve this on calculators and it will give you the R0 value, that is 146.2 Kelvin per watt. Now the total resistance in the second case is equal to Ri plus R1 plus R2 plus R0. And simply add it and you will get the total thermal resistance for the second case, that is 356 Kelvin per watt. Now the amount of heat transfer with contact lens is equal to change in temperatures divided by thermal resistance between these. Inside temperature is 37 centigrade, outside temperature is 21 centigrade. You have a total thermal resistance in the second case, that is 350. Let's solve this on calculators and you will get the amount of heat transfer. The second case, when the contact lens is provided over the cornea of the eye, and that is 0.0449 watt. Multiply with 1000 to convert into milliwatt, and that is equal to 44.9 milliwatt. If you compare, the amount of heat transfer in the second case is more as compared to the first case. In first case, the amount of heat transfer is less. Why it happened? Because the R3 value, the outside of the contact lens, is less than the critical radius. That's why more heat transfer occurs. I hope you understand. If still there any confusion, you can ask in the comment section. Please subscribe my channel if you haven't subscribed. Thank you so much.